Welcome to the problem-solving set on the chi-square test. If two big D, big E, little e plants are crossed to give the following phenotypes in the offspring, where the total number of offspring is 1600. Part A. If D and E are completely dominant to little d and e, what are the expected numbers of offspring for each phenotype if these two genes are unlinked? So let's write the cross again. You have big D, big E, little e, times another individual with the same genotype. And if these genes are unlinked, that means that this is a simple dihybrid Mendelian cross. And that's because both parent individuals are heterozygous at both gene loci. Now, what are the phenotypic ratios in a dihybrid cross? You have 9 to 3 to 3 to 1 ratios, where 9 is the dominant phenotype for both genes, 3 is the dominant phenotype for one gene and recessive for the other 3 is opposite, and then the 1 represents the recessive phenotype for both genes, so little d, little e, little e. Now if there are a total of 1600 progeny, and these adds up to 16, that means we're going to multiply by 100 to get our expected numbers. So for this dominant phenotype, you would expect 900, 300 for this, another 300, and 100 here, which totals 1600. So for the chi-square analysis, these are our expected numbers, if using the null hypothesis that our genes are unlinked. So null hypothesis is that D and E are unlinked. Okay. Now for part B, it said based on the hypothesis that these genes are unlinked, what is the chi-square value? So remember that the chi-square formula is the summation of observed minus expected squared over expected. And we're going to do this for each of the 4 classes and then sum them up. So for the first phenotypic class, which is dominant at both genes, we're expecting 900. But if you look up here, dominant at both genes, we see 910. So we'll do 910 minus 900 squared over 900. The second class, which is dominant for D and recessive for E, we see 320, and we expected 300. Square that, divide by 300. For the next class, we have recessive for D and dominant for E, and we see 280, and we expected 300. Square that, divide by 300. And finally, for the last class, where it's recessive for each gene, we see 90, and we expected 100. So divide by 100. Now if you want to follow along and do this on your calculator, or you could just look at the calculator here, I'm going to do each of the 4 classes, and then I'll sum those 4 numbers later. So you have 910 minus 900 is 10, squared is 100, so 100 divided by 900, you get 0.111. So let's write 0.1. Now the next number, you have 320 minus 300 is 20. When you square that, you get 400. 20 squared is 400. And now you're dividing by 300. You get 1.333 repeating. Okay, the next class, again, 280 minus 300 is negative 20, but when you square that value, you'll get a positive 200, which divided by 300. I'm sorry, when you square that 20, you'll get 400, which divided by 300 again is 1.33 repeating. And finally, the last one, 90 minus 100 is negative 10, squared is 100, so 100 divided by 100 is just 1. Now let's add these all together. So we have 1.333 repeating. I like to just put a lot of decimal places just to be more accurate. Plus another 1.33333 repeating. Plus 0.11111 repeating. Plus 1. So total, we get 3.77, so we can say 3.78. So the summation of that is 3.78, and that's our chi-square value. So chi-squared, 3.78. Now for C, based on the calculated chi-square value, would you conclude that the genes are linked or unlinked? So for this, we're going to have to look at a chi-square table. However, let's first determine what our degrees of freedom are. Remember that degrees of freedom equal to the number of classes minus 1. If you look at the number of phenotypic classes we have 4. So when you say that df equals n minus 1, n here equals 4, and therefore our degrees of freedom equal 3. So let's look at the chi-square table. We're going to look at the degree of freedom equal 3 and see where 3.78 lies. Okay, so we're looking here for degrees of freedom 3, and where does 3.78 lie? It lies somewhere here. So we have 3.78, which means that between 10% and 50% chance that these deviations are just due to random chance. So that means it falls under the cannot reject the null hypothesis. So if we can't reject the null hypothesis, which remember was that they're unlinked, that means we have to accept it, so we're going to say that these genes are unlinked. Problem 2. A true breeding dark red flowering plant is crossed with a true breeding white plant to obtain F1 offspring that are pink. When the F1 plants are selfed, 250 pink plants, 120 white plants, and 130 red plants are observed. So this total of 500 plants. So A. If it's hypothesized that flower color is determined by a single gene, and red flower color is partially dominant to white flower color, what are the expected values for the number of offspring of each phenotype? So let's define our alleles first. For true breeding red, this means that they are, let's call it C for color, with the superscript R for red. So CR equals red, and CW for white, CW equals white. Well, when mixed, CW, this yields a pink plant. So it's saying this is a single gene and red is partially dominant to white, or it's just incomplete dominance. So it says what is the expected values for the number of offspring of each phenotype. Now this is talking about a pink versus a pink, which would be CRCW times CRCW, which is they're both heterozygous and it's a monohybrid cross. So you would get 1/4 CR, 1/2 CRCW, and another 1/4 CW, which in turn would be red, pink, and white. Now if there's 500 offspring, what do these percentages account to? So 1/4 of 500 is 125, 1/2 is 250, and another 1/4 is 125. So for chi-square analysis, these are our expected numbers. Okay, so for B, it says how many degrees of freedom are there? Well, we have 3 phenotypic classes. Remember that degrees of freedom is the number of classes minus 1. So 3 minus 1 equals 2. And what is the calculated chi-square value? Okay, so remember that chi-square is equal to the summation of observed minus expected squared over expected. So for the first class, red, we observed 130 and we expected 125. So 130 minus 125 squared over 125. For pink, we expected 250, and we saw 250. So we know that this is going to equal 0 because 250 minus 250 is 0, and therefore that whole term will be 0. Now for the white class, we observed 120, and we expected 125. So 120 minus 125 squared over 125. So we have 130 minus 125 is 5, squared is 25, so 25 divided by 125 equals 0.2. The second term is 0, as we said. And the third term, 120 minus 125 is negative 5, squared is positive 25, again over 125 is 0.2. So therefore the total chi-square value is 0.4. It says for D, what would you accept or reject the hypothesis that flower color is a single gene trait? So remember, our null hypothesis is that it is a single gene trait. So now we have our chi-square value of 0.4 and our degree of freedom of 2. So let's look at the table to see where this lies. So we have degrees of freedom of 2, and our chi-square value is 0.4, which is somewhere in the middle here. 0.4. So that means that between a 50% and 90% chance that these deviations from our expected numbers is just due to random chance, and therefore we cannot reject the null hypothesis. Which means, because our null hypothesis was a single gene and we can't reject it, means that we would accept the hypothesis that it is a single gene trait. Problem 3. The cross big A, big B, little b, times little a, little b, yields the following, with a total number of offspring of 1,000. Part A. Big A and big B are completely dominant to little a and little b. What are the expected number of offspring of each phenotype if these two genes are unlinked? Well, let's look at the parental cross. You have a dihybrid individual times a homozygous recessive for both genes individual. So what are the gametes that these individuals can produce? This homozygous recessive, if unlinked, can only produce a little a, b gamete. If unlinked, this first individual can produce big A, big B, little a, little b, big A, little b, and little a, big B. So 4 different gametes. If these genes are unlinked, that's what they can produce. So, if you're crossing these two individuals, it's asking what are the expected number of offspring of each phenotype? Well, there are 4 possible phenotypes that this cross can give, and because this homozygous individual can only make 1 gamete, that means there's a 25% chance of each of these phenotypes. So, a quarter chance of this gamete, this one, and this one. Now, if there's a total number of 1,000 offspring, that means you would expect 250 offspring of each phenotype. So you would expect 250 AB, 250 little a, big B, 250 big A, little b, and 250 little a, little b. So for chi-square, these are our expected numbers. Okay? So we'll write 250 for all. Now it's saying, what is the calculated chi-square value? Again, chi-square is the summation of observed minus expected squared over expected. So the first class, dominant, big A, big B, we expected 250, and we saw 300. So 300 minus 250 squared over 250. The second class, little a, big B, we expected 250 as always, and saw 175. So 175 minus 250 squared over 250. The third class, again, expected 250, and we saw 200. So 200 minus 250 squared over 250. And finally, the last class, we saw 325 and expected 250. So 325 minus 250 squared over 250. So let's actually calculate this. The first, 300 minus 250, sorry. Okay, 300 minus 250 is 50. So 50 squared, 2500, divided by 250 is 10. So we have 10 here. 175 minus 250 is negative 75. And when you square that, you get 5625 divided by 250 is 22.5. The third, again, it's 200 minus 250, negative 50, squared divided by 250 is going to give you 10. And for the last group, 325 minus 250 is 75, squared divided by 250 is 22.5. So total, you have 10 plus 22.5 plus 10 plus 22.5, you get a total of 65. So this is your chi-square value. And again, the degrees of freedom are n minus 1, and there's 4 different phenotypic classes, so 4 minus 1 equals 3. Based on your calculation, are the genes linked or unlinked? Now remember that our null hypothesis is based on the fact that these genes are unlinked. So let's write that here. Null hypothesis equals unlinked. Okay? So we have a degree of freedom of 3, so let's look where 65 falls in that category. So we have 3, and where does 65 fall? It falls way down here, which means that less than 0.1% chance that these deviations are due to random chance, which means that we reject our null hypothesis. So if this is rejected, that means that these genes are linked. Problem 4. A feline geneticist was mating a striped cat with a spotted cat. She predicted a phenotypic outcome of the traits she was observing to be in the following ratio: 4 spots only to 3 stripes only to 9 both stripes and spots. When the cross was performed and she counted the individuals, she found 4 with stripes only, 5 with spots only, and 8 with both. Using the chi-square calculation, did she correctly predict the outcome? So let's write the phenotypes. So we have spots only, stripes only, and spots and stripes. So what she predicted, which would be our expected numbers, she expected 4 with spots only, 3 with stripes only, and 9 with both. She observed 4 with stripes only, 5 with spots only, and 8 with both. So let's do the chi-square analysis. Chi-square would be the summation observed minus expected squared over expected. So this would equal the summation of 5 minus 4 squared over 4 plus 4 minus 3 squared over 3 plus 8 minus 9 squared over 9. So let's do these calculations. 5 minus 4 is 1, squared is 1, over 4 is 0.25. 4 minus 3 is 1, squared again is 1, out of 3 is 0.333 repeating. And 8 minus 9 is negative 1, squared is positive 1, and 1 out of 9 is 0.11 repeating. So what is the total chi-square value? You have 0.25 plus 0.333 repeating plus 0.111 repeating, and you get 0.6943, which we can round to 0.7. How many degrees of freedom there are? Well, there's 3 different phenotypic classes, which means our degree of freedom is going to be one less than that, which is 2. So let's look at the chi-square table. We have 2 degree freedom, and this chi-square value is 0.7, which would lie somewhere in here. Oh, I'm sorry. It would actually lie somewhere between here, which means there's a 50 to 90% chance that the deviations from expected values are just due to random chance, which means that we cannot reject the null hypothesis. And this means that she did correctly predict the outcome, so yes, she did. Problem 5. A trihybrid individual is crossed with a homozygous recessive individual, and the offspring have the following phenotypes. Assume big A, big B, and big C are dominant to little a, little b, little c, respectively. So the offspring phenotype, the total offspring is 800. It says, what is the expected number of progeny for each phenotype if the genes are unlinked? Well, let's look at the parents that we're crossing. We have a trihybrid, which means heterozygous at all 3 genes, and we're crossing it with a homozygous recessive at all 3 genes. So what are the gametes that these individuals can produce? This homozygous recessive can only produce an A, little b, little c gamete. And remember, this is under the assumption that these genes are unlinked. Now, how many gametes can the first individual produce? Well, let's do the shortcut we did early on in chapter 2. So for the A gene, there's 2 different alleles, so we'll write 2. For B, 2 different alleles. And for C, 2 different alleles. When you multiply that across, that means there are 8 different gametes that can be produced. And these gametes, when meeting with this one, are what will determine phenotype because little a, b, and c are recessive. So, if there's a total of 800 progeny, and there's 8 different gametes or 8 different phenotypic classes that can be produced, how many of each will we expect? Well, we would expect 800 divided by 8 different phenotypes, or 100 of each. And that's, again, if they're unlinked. So what is the calculated chi-square value? Chi-square, again, summation observed minus expected squared over expected. Now there's 8 different classes, so this might take a little while. Okay, so for the first class, remember these are observed up here. And for expected, we're just going to say 100 for all of them. Okay, so for big A, big B, big C, we observed 95 and expected 100. Okay, for the next phenotypic class, we observed 105 and expected 100. For the next, we saw 107 and expected 100. Then we observed 83. Then 110. $90. And the last 2 are 105 each. Okay, so let's do these calculations. Okay, so 95 minus 100 is negative 5, squared is 25, and 25 out of 100 is 0.25. For the next one, 105 minus 100 is 5, squared is 25, over 100 is 0.25. 107 minus 100 is 7, squared is 49. Out of 100 is 0.49. Then 83 minus 100 is negative 17. Squared is 289. And divide that by 100, you get 2.89. Then 110 minus 100 is 10. Squared is 100. And 100 out of 100 is 1. Same goes for 90 minus 100 is negative 10. Squared is 100. Divided by 100 is 1. And for these, 105 minus 100 is 5. Squared is 25 over 100 is 25. So the last two will be 0.25. Okay? Now let's add these all together. Okay, we have 0.25 plus 0.25 plus 0.49 plus 2.89 plus 1 plus 1 plus 20.25 plus 0.25, which gives you a total of 6.38. And this is the chi-square value. Now what are our degree of freedom? Well, there's 8 phenotypic classes of the offspring, which means there are 7 degrees of freedom. So let's look at a chi-square table. So we have 7 degrees of freedom, and our chi-square value was 6.38. So 6.38 would fall somewhere in here, which means there's between a 10 and 50% chance that the deviations from expected values are just due to random chance, and we cannot reject the null hypothesis. So, cannot reject null. And remember, our null hypothesis is always that the genes are unlinked. And because we can't reject that, means that we will accept that the genes are unlinked.